Hello, all of my statisticians to be. This is PS Professor Sampson from Professor Sampson PS. I love math. Again with another statistical banger. We just banging and banging and banging, right? So anyway, it is time for us to hit this one up again. We are going to do our second problem. The problems take so long, as you know, for hypothesis testing with two population means when the sigma is unknown for an independent sample. All of that, those of you in stat, know what's up, know what that means, okay? But real quick before we go, first, a word from our sponsor. Please don't forget to comment, like, and subscribe over here, down here somewhere in pink, since pink is my favorite color, right? Don't forget to comment, like, and subscribe so I can keep these statistical bangers going so that you can get your A in your class and keep it moving. So enough begging for subscribers, which I need 1,000. The road to 1,000 is yours. But anyway, so let's go ahead and hit this up and get ourselves started. So I have an example already ready for you. So I'm going to do my usual and share my screen so we can begin getting this banger off, okay? Okay, so let's get this one started. You know, I'm going to read the whole thing, but as you know, I don't usually read them. I just jump in and get the numbers. So let's get it. While running some quality control tests, a manager at a factory that makes potato chips noticed a difference in the mean bag weights for chips coming from two different production lines. So this is real life application of statistics and what's going on. To see if the bags in line A did actually have a mean weight lower than those in line B, he randomly selected some bags from each line. His results are given in the following table. If he assumes that the population variances for the two lines are different, can he conclude at the 0.10 level that the mean weight of bags from line A is lower than the mean weight of bags from line B? Okay, so let's get this started. In this case, you know I'm going to first write down my knowns. So line A, let's not try to write in erasing. Line A, right? We have N1. Everything is given to us here is going to be 20, right? The mean of line A, which means the bags that came out of line A. So this is the sample mean, not the population mean, just that sample. So that's going to be X bar. And likewise, we're going to have our sample standard deviation, the standard deviation of that line. S is equal to 15.91. Okay. Then we have line B. Line B, you have N2, and we're going to have the same thing, N2 meaning our second line. And then our standard deviation of the second line is 13.21. As I always say, if you can't find the answer here, then you can't find the answer because you have everything that you need. As you see, I wrote alpha on the side. So we have all our numbers out of here, all right? And I'm just going to underline our conclusion. Should have highlighted it because my line's going everywhere, but you get the point. So anyway, that's all the numbers we have. So the question is, first we're going to write our null hypothesis. I'm going to write it over here. So our null hypothesis is what? Is that the means are equal. So we always assume that our means are going to be equal. That's our null hypothesis, all right? That the means are equal, okay? That there's no change, that there's no difference between the lines, because that's what we want to assume. If he's doing these potato chips, he want to assume first that the means are the same, all right? But he's trying to conclude his conclusion, his test is can he conclude that the mean weight of line A, right, is lower than the mean weight of line B, okay? So that's our alternative, all right? Now we're going to move on to our test statistic. Now, what is our test statistic going to be in this case? All right. What is our test statistic going to be? Now, remember, we base our test statistic. We're looking for a T or Z because that's what applies to mean. So we're trying to figure out what our test statistic is. So is it going to be a T or a Z? How do we figure that out? Well, we figure that out from saying, okay, do we know the population standard deviation or do we not know the population standard deviation? Unlike the last one video, which would be a test at the end of the screen, we knew the population standard deviation, so we use the Z. But on this one, we do not know the population standard deviation, so this is going to be a T. And as I stated before, or as you should know, the formulas for the Z and the T are the same except S and sigma change, okay? So S and sigma change. That's the only thing that changes in the formula. Now, not that you have to memorize, at least most instructors will give you a formula sheet or something like that, okay? So let's just write down our formula for T just to get it written down. X bar 1 minus X bar 2, and I'm gonna go through this pretty fast. Well, as fast as I can write. Love those straight lines, right? Trying to make it bigger this time. Right, over n sub 2. That was dead space while I was writing. I guess I could fast forward if I knew how to do that, right? So anyway, let's keep this going. This is the formula. Now, the only thing that would be different, let's say if you had the population standard deviation, that would go here. So it really doesn't matter. Your instructor won't know, unless they're looking at your work like I do. Look, you needed to use a Z or a T, and the student will say, well, I got the number right. Well, of course you'll get the number right because the numbers go in the same place for the test statistic. But that doesn't matter. Ultimately, you need to know whether you're using a T or a Z. So we're going to plug in these numbers here into our equation and see what we come up with once we plug in all these numbers. Okay, I didn't want to make the video longer by having you watch me put in the numbers, but as you can see, 309.63 minus 311, all over that stuff. So I just plugged in all the numbers, which you can do on your own. So now let's click over to our calculator and find out what our test statistic is. So again, now this is different, so I didn't go through this. So we're going to go to stat and we're going to go to test, and we need a t-test. We need a 2-sample t-test, not a z-test. So this time you're hitting number 4. And again, we're given stat. And then we're going to go in and plug in all our numbers, which I can do right now. So the first thing is x sub 1, 309.63. Right? And then the standard deviation of that is 15.91. N was 20. Plop these numbers in. 311.87. What was that? 13.21. And N is 15 for that one. All right, always double check your numbers. Hopefully my numbers are right. And as you can see, our original alternative was, right, was mu sub 1 is less than mu sub 2. So mu sub 1, we need the less than mu sub 2. Do not worry about pooled data. We're not using pooled data, so that's a no. All right. So now let's go down to calculate. All right. So now let's see. Now a t, we use 3 decimal places because that's what's on the chart and that's what we're going to be comparing it to. So this t came out to be negative 0.455 if you round appropriately, 0.455. Right? So that's our T negative 0.455. And as usual, you see I wrote down T test statistic. Okay, T test statistic, because there's difference obviously between your test statistic and your critical value. Okay, so again, we're going to do as we did before. We're going to do both methods depending on your instructor. This one actually I have a three methods. We're going to have the critical value method. Okay, that means we're going to compare the critical value. Always draw a picture so you know what you're looking for. My picture sucks, but it's picture nonetheless. So this time we're looking for area to the left over here of our critical value. So T-crit. Now remember, we said that our alpha was 0.01, which is good. Remember, whatever we read off the chart will be what we get because your alpha is on the chart, all right? So let's see what happens. Can we do that? Let's check it out. So now we need a T-chart, which I definitely have one here. Okay, so here's our T-chart. Again, this is a one-tail test, so we don't have to worry about two tails. So again, we need our degrees of freedom. Do you recall? Now, different places do degrees of freedom differently. In my course, the degrees of freedom is going to be the lower of the two. Now, depending on your instructor, you might have to get clarification, but for mine, it's going to be the lower of the two. So the degrees of freedom, the line A, right? The degrees of freedom is 20, right? Minus 1, which is 19. All right, and for B, it will be 15 minus 1, which is 14 degrees of freedom. So I'm going to use the lower of the two. So my degrees of freedom is going to be 14. All right, degrees of freedom is 14. So now let's look back at our T-chart to check it out. So we got our degrees of freedom, which is 14. I can move this up a little and then blow it out. All right, so you should have your chart. So the degrees of freedom is 14, right? And we're looking for 0.10, all right? That was our significance, that was 0.10. So 14, right, and go over, here's 14. And right there, 0.01. 1.345, okay? Remember, this is right tail, 1.345. So let's go back. But this is area to the left. So remember, that's going to be negative 1.345. You have to be smarter than your chart, okay? You have to know that area to the left of your mean is negative. So this is negative 1.345. So now let's put our test statistic. You see, we got 3 digits for both of them. Now, where would negative 0.455 be on this number line? Well, it's going to be in this area, right? Because if you go more negative, you're going to get -2 or whatever. It's going to be over here. So negative 0.455 is over here in the what? In the failed to reject region. All right, in the failed to reject region. So we're going to fail to reject the null hypothesis. So we don't know anything. What do you know when you fail to reject the null hypothesis? We don't know anything. We don't have enough evidence to say that it is or it isn't. That's what fail to reject the null hypothesis is, which we'll write in our conclusion in a minute. All right. So let's go on with the other two methods. So for the p-value method, there are 2 ways to do it. You have the p-value method range and the p-value method, all right? What does that mean? Well, when you have a T-chart, if you take a look at it, there's no area under the curve, right? There's no area under the curve in a T-chart, all right? No area under the curve, so you can't get an exact p-value like you can when you're using a z-chart, all right? So for a t-chart, since there's no area under the curve, what we can do with our t-chart is we can find what's known as a p-value range. If you need to get an exact p-value, then you have to use statistical programming or software or your calculator to get an exact p-value. But we can get a p-value range from our chart. Just wanted to emphasize that. So depending on your instructor, you can determine whether they're going to allow you to get a p-value range, or you can get a p-value, an exact p-value. So I'm going to show you both of them. Let's start with the p-value range. How do we find our p-value range? Well, of course, we go to our chart. So let's take a look at our t-chart again. All right, so here's our t-chart. And we want to figure out what the range is going to be. So a little bit like the z-score, we go back and we find what our t-test statistic was, all right? So our t-test statistic was negative 0.455. We know it's going to be 0.455 when we read it off a t-chart, because a t-chart is area to the right. So 0.455. So we go to our t-chart, and at 14 degrees of freedom, we look for where 0.455 would fall, all right? So 0.455 would fall in between 0.258 and 0.692, correct? That's where 0.455 would fall, right? So that's between 0.40 and 0.25, but you have to reverse them because it's from higher to lower. So your p-value range is between 0.25 and 0.40. All right. So your p-value range is between 0.25 and 0.40. So let's put that down. So our p-value range is between 0.2500 and 0.400. Remember, 4 decimal places for p-value. All right. And we're going to compare that to what? To our alpha, which is 0.10000. So look, 2,500 and 4,000 is what compared to 1,000? 2,500 and 4, between 2,500 and 4,000 will be greater than 1,000. So it's not lower than. So again, we failed to reject based on the p-value range. All right. If you wanted to know an exact p-value, we got that in our calculator. The exact p-value is 0.3262. Right. And again, that is greater than 1,000. Okay. And as you can see, 0.3262 is in between 2,500 and 4,000. Okay. So you have the critical value method, the p-value method, and the p-value method range method. So either way your instructor asks you. So the final part is the conclusion. All right, what is going to be our conclusion here? Well, let's see. So what do? We fail to reject. So do we have sufficient evidence? No, we don't have sufficient evidence. So there is not sufficient evidence to support the claim that what? We look back up at the top into the words that we're working on, that the mean weight, right, of bags from line A, right, is lower than the mean weight of bags from line B. Okay? So that is your conclusion. That is the conclusion that you take to the person who asks the statistician, or that the statistician takes to the person who asked them, hey, can you check out our machines and tell me if they're different? So for this one, we tell them there is not sufficient evidence. We don't have a conclusion. We don't really know with this amount of data if there's a difference. There could be a difference. There could not be a difference. We currently don't know if there's going to be a difference. And that's what we need to state to them after we do all our statistical information to figure out what's going on. So we took care of that when we did our hypothesis test for two population means for unknown, for two samples when the population mean is unknown and we have independent samples. So if you want to know what happens when the population means are known, you can check out my other video, which is probably over here somewhere. All right, and then we have another one. We're going to move on in our hypothesis testing and talk about dependent samples, because these two samples, remember, they were independent, line A and line B, independent of each other. They had nothing to do with each other. So when you're looking at your problems and statistics and no one's there to read, you have to determine, are these samples independent of each other? And they are. This was line A and line B. And my last example, all right, talked about, I forgot what that was in reference to, but it's had independent samples within and of itself also. So that takes care of that. Again, this is Professor Sampson at PS I Love Math. Please don't forget to click the subscribe button, all right, so you can give me some love, and make sure you comment and like this video so that other people can know that this video is something that helped you out. Thank you. This is PS I Love Math.